Shalom, my children. So today we are going to go on to the ideal gas chapters. This is the last chapter that is typically covered in General Chemistry 1. And so we'll make our most of it. We'll break this down probably into 3 videos. Video 1 will be discussing the basics of the ideal gases and their individual gas laws. Video 2 will most likely be discussing some of the other aspects of the ideal gas law. It'll be a shorter one. And video 3 will be looking at the theory and some of the harder aspects of this chapter. Okay, let's go ahead and get started. Okay. So the first thing we need to talk about is gas. What is it? As we see an image borrowed from Wikipedia of a gas in motion. You can see the individual molecules bouncing around, ricocheting. There's some blue, there's some red, but they're mixing without a problem. Some are going fast, some are going slow, and as a fast one runs into a slow one, they change speeds as the energy is transferred in what we call a inelastic collision. So, gas. Gotta remember, a solid is a compound of definite volume and definite shape. A liquid is one that has a definite volume but an indefinite shape, meaning it will easily smush out to fit any container it's in. And a gas is one that has neither definite volume or definite shape. So not only it is compressible, but it's also, it will fit whatever shape you have. Well, gases are chemically very different in reactivity. They are often very similar in the physical properties. Most gases are colorless. Most are odorless. As we'll learn in Avogadro's law, they all approximately the same size molecularly. This is due to the gas dispersiveness. That really a gas is made up of mostly empty space with the molecules bouncing around. They're not all packed tightly together like you would see in a solid or even a liquid. That essentially, because of this, the gases are essentially the same size. Even though the individual molecules may be bigger and smaller, the gas as a whole takes up the same amount of space. Now they will expand to fill any container, yet they are highly compressible. And unlike a liquid, gases will readily mix regardless of the other gas it's mixing with to make a homogeneous mixture. Liquids will not do this because of the electrical character. Oil is very nonpolar. Water is very polar. Water and oil do not mix. If I try to mix, very different liquids based on its polarity will not mix. They form our micelles. They form our lipid bilayers. They form various different shapes in order to keep regions of opposite polarity away from each other, regions of different polarity away from each other. But gases will mix perfectly. Doesn't matter what you have. Chlorine gas, water, oil vapor, methane. They're going to mix and bounce off each other just fine. That's the nature of gases. Now, before we get into things, we need to talk about units. We previously looked at pressure ever so briefly when we talked about thermochemistry. That's because pressure is a force, except this is a force applied over a very defined area. So it's not just a single point. It is the area of that force being pushed down. So if I have my whole hand pressing down on something, the force of my hand over the area that my hand is pressing. If I were to increase that force, I can increase the pressure by changing it to just a single finger, pushing down. So it's the area of the pressure is concentrated. Now, when we talk about pressure, we're going to talk about atmospheres, ATM, bars, the barometrics, torricellis, the torrs, millimeters of mercury, mmHg, pascals, or PA, or pounds per square inch, PSI. All of these are units of pressure. So why do we have 5, 6 different units all dealing with the same concept? I mean, it's one thing if you're like meters per second as opposed to kilometers and miles per hour, but in reality we have our basic English units and our basic metric. The metric, here we have so much of a grab bag, it's hard to really wrap our heads around it. But so, what's the deal with that? My bad Seinfeld impression. So, if you look right here, we have conversions. You can convert an atmosphere to a millimeter of mercury by just a factor of 760. You can also convert an atmosphere into torr by the same conversion factor. In terms of pascals, 1 atmosphere is technically 101. What would it be? Yeah, 101,325 pascals. And a bar, it's by 1.01325, kind of like the protons to neutrons. They're not quite equal, but they're pretty darn close. Of course, to convert an atmosphere to a PSI, it's just 14.7. But it's possible to convert one to another rather easily. Now, where do we get all these units from? All units must be derived from something. We get some way to compare it to. A meter has to be compared to something to define what is a meter. It used to be a certain amount of distance. There's so many meters around the Earth. We use that as a comparison. Now we use it to its certain amount of distance that the speed of light travels. The speed of light travels so many meters in a second, and we use that justification for a meter. Just like a foot used to be someone's actual foot. That we used to, like, when you talk about a horse is so many hands high. That someone's hand had to be initially used to quantify that. So, with that in mind, how do we quantify these units? How did we come up with a Pascal is this much? Well, this is how one of them gets initially derived. And this is some heavy physics to get here, but here's how we do it. It's that every gas particle contains matter. Because it contains matter, it has a mass and is subject to gravity. Now, gas particles bounce in all directions, and this is due to their low density. They are able to essentially fight gravity, that they have enough kinetic force that the upwards force is greater than the downward effect of gravity. But that does not mean they do not experience gravity. They still are being pulled downwards, and they have weight. It's just in the downward direction, they're moving faster by 9.8 meters per second squared. And if they're moving upwards, they're moving slower by 9.8 meters per second squared. They're being pulled up or pulled down. So, because a pressure is defined as a force over an area, we want to figure out what force would the Earth's atmosphere apply over a specific area. So the specific area we're defining is we're taking an imaginary 1 by 1 meter box. 1 meter being the standard SI unit for distance. So 1 meter by 1 meter box, and we stretch it all the way out until we reach no atmosphere. And we imagine this imaginary box is filled with gas, all the gas that would normally be filled with a box that reaches all the way into outer space. Well, fill that with gas, it would hold approximately 10,000 kilograms worth of gas. And all 10,000 kilograms worth of gas experiences gravity. Now, because a force is a mass times an acceleration, that 10,000 kilograms multiplied by gravity is approximately 10 to the 5th kilogram meters per second squared. Technically, it's 9.8 times 10 to the 4th, but that's close enough. Now, because it's a force and we're dividing by the area it's applied under, that 1 by 1 box, that gives us a unit of 100,000 Newton meters squared. Now, Newton meter squared is perfectly reasonable, but in order to simplify this, we call this a Pascal. 1 Newton per meter squared is a Pascal. That's the metric unit and the SI unit for pressure. Now, this is named after the French scientist and mathematician Blaise Pascal, who had developed this. Now, once again, oftentimes when we're dealing with really big or really small numbers, it gets very confusing for our stupid little monkey brains. So in order to simplify that, we said 100,000 pascals is equal to 1 barometric unit, or a bar. A bar is a metric unit. You can have millibars, you could have kilobars, you could have microbars, but it's not considered the SI unit. But it will be one of our standard units that we will use very often when we measure gas rather than pascals. But so we calculate that. Just fine. Now, with that in mind, around the same time, another scientist, Evangelista Torricelli, was doing similar experiments testing the weight of air, because at the time many of the scientists believed air to be weightless. In the process, he invents the simple barometer, which essentially is just a long graduated tube. He fills this container up with mercury. Quicksilver is how it was known. But he fills it up and inverts it into a tub of mercury. Now, because of the nature of that, air cannot get into the tube. So there's nothing replacing the mercury. So the mercury will slowly drain out of the tube, creating a vacuum in that tube. However, not all of the mercury will drain out. Some amount of mercury will remain in there as the vacuum is pulling up and the air pressure is pushing down on the mercury, forcing it into the tube. You'll get a balance point where how much mercury can fit into that tube, how much mercury will drain out. And this was measured. So he measured this at the sea level and found this to be in Paris. They found this to be 760 millimeters, or essentially 76.0 centimeters, thus giving us the unit 760 millimeters of mercury. Now, millimeters of mercury is a literal figurative measurement of the mercury height. However, Torricelli was honored by giving the millimeter of mercury equal to a torr. Torr is kind of like the Fahrenheit of pressures. A little bit unusual, but still very useful in that it's very small changes can be recognized a lot easier than, say, the bigger unit. Now, this pressure was the same pressure at sea level for Paris and many other European cities of the time of a similar latitude, and thus it was set as the standard atmospheric pressure. 1 atmosphere is equal to 760 torr. Now, due to the variety in weather and latitude, pressure will actually vary. So not every country is going to have 1 atm as their pressure, but they should all have something relatively close. It's hard to define what is better, 1 atmosphere, 1 torr. 1 atmosphere or 1 bar. But some people like 1 because it's easy to convert. Some people like another because it's probably the more common one. You're feel free to make your own decisions. And of course, PSI is the American bastard child of the two, because a force is a Newton per meter squared, a force applied over an area. Well, the English unit for force is pounds of force. Pounds of force applied over a square inch. So English unit for force, English unit for distance gives us PSI. So it's easy enough to convert between the two. Now, so we're getting into now the laws, our basic laws. A law, remember, is a statement of fact without really an explanation. Boyle's law, created by Robert Boyle, simply states that if you keep a gas's temperature constant, the pressure of that gas is indirectly proportional to the volume, meaning a higher volume gas has a lower pressure. A higher pressure gas has a lower volume. It does not go on to explain why. It's just simply a statement of fact. And in fact, we can write a mathematical relationship that P times V equals a constant. And we can write, because this is equal to a constant, we can write an equation that says P1 V1 equals P2 V2. Basically, that the pressure and volume of a gas is proportional to the pressure and volume of a gas under different situations, assuming the same gas. Well, how, I'm maybe getting ahead of myself, but how would we explain this? Remember that pressure is a force. Well, how do gas create force? If we go back to that first major slide where the particles are bouncing around in that box, each of those collisions generates a force. Now you're calculating the total force applied over the area of that wall of the box where they're colliding there. So understanding that the gas moving at a more or less constant speed colliding with the side of the box. Well, if I were to shrink the size of the container, the gas moving at more or less the same speed would have more collisions. More collisions means more pressure. So by looking at that, the smaller the volume, the higher the pressure. The larger the volume, the lower the pressure, because there will be less collisions. Charles, working along with another scientist by the name of Gay-Lussac, developed these further relationships, that at a constant pressure, volume is proportional to temperature. Gay-Lussac came up with at a constant volume, pressure is proportional to temperature, but we kind of forget him because all you need is volume and temperature. So basically saying as volume were to go up, well, actually as temperature goes up, volume should go up. Temperature goes down, volume should go down. And we see that directly. You put a balloon in the freezer, it will shrivel up. As you allow it to warm up back to room temperature, it will expand to its original volume. So we can write a direct relationship of V times a constant is equal to V equals a constant times T. And we can write a relationship where V1 over T1 equals V2 over T2. Basically, the volume temperature relationship at one situation must equal the volume temperature relationship of a second situation. Please note, when we talk about temperature, we are talking about temperature in Kelvin. We are always going to be talking about temperature in Kelvin in this situation, mainly because gases don't cease being gases just because it's at 0 degrees Celsius or 0 degrees Fahrenheit. So we need to account for the fact that as temperature goes down, it will affect it, but the gases will not necessarily go negative because the temperature is negative. So you need an absolute temperature that never goes negative. So how can we imagine this? Well, temperature is directly proportional to kinetic energy, our energy of motion. Hotter things move faster. So if a temperature were to increase, so would the pressure. However, as we just learned, pressure is indirectly proportional to volume. So if I want to keep the pressure from changing, the volume must increase. Objects moving at faster speeds need more area to run around in. A hamster only needs a small cage. Small object, small thing. A dog needs a full yard. If you had a horse, that same yard in the city is not going to cut it. You need a large, you need like a farm in the country. The faster they're moving, the more volume they need to take to be happy, to be able to roam, as you will, without collisions. So with that in mind, we can look at a combined gas law. We put these two gas laws together, we can relate them together. That pressure, volume, and temperature of the first situation is equal to pressure, volume, and temperature of the second situation. We can easily relate them if they're held under similar conditions. In problems where we're using this, all the info will be given except for one variable, and we're trying to solve that one variable. So a gasified fuel is combusted at 1 bar. 1 bar. And temperature of 20 degrees C in a piston chamber with a compressed volume of 520 milliliters. If under combustion, the temperature changes to 210 degrees C and the gas expands to 1.1 liters, what must the pressure now be? One of the key features here is that we need to convert everything into the proper units. 1 bar, I can leave that in bars. 20 degrees, we need to add 273. We need to add 273. So this becomes 293. This becomes 483. This is milliliters, this is liters. I'm going to convert this into milliliters. So 1100 milliliters. So P1V1 over T1 equals P2V2 over T2. So 1 times 520 divided by 293 equals P2 times 1100 all over 483. Kelvin, Kelvin, milliliters, milliliters, bar. So, to solve for this, I'm going to need to get that to that side and that to this side. I'm solving for P2. So, let's start with here. see. Okay. 1 times 520 divided by 293. Then I'm going to multiply by 483 and divide by 1100. And I get the pressure has actually dropped. Dropped to 0.779 bar. You may be saying, what? But it heated up. However, the volume expanded by a little more than double, while the temperature did not double. It may look like it had gone from 20 to 210, but in terms of Kelvin, not actually a full doubling. And so that gives us that. Now, there's one last law we need to learn, and that is Avogadro's law. Named after Amadeo Avogadro. You probably know him from Avogadro's number. His law simply states that at a constant temperature and pressure, moles of gas are directly proportional to the volume. That he found that if I wanted to, say, completely react hydrogen and oxygen, I could fill up a balloon with hydrogen to be twice as big as a balloon of oxygen, and it would completely react to form pure water. Now, if you remember our chemical reaction from last chapter, 2 hydrogens are needed to react with 1 oxygen to make our water, to make our 2 waters. So we found that volumes of gases were essentially proportional to the atomic count, which is essentially proportional to the moles. Found out that if you had more moles, you needed a more volume. And so we could directly relate volume to moles by the equation. And in terms of gases, it's easy to understand. You increase the number of items, you're going to have a fuller container. It's going to be more collisions. However, if I do not want more collisions, I need a bigger container. Just like a box, if the small box is overflowing, get a bigger box so it's not as stuffed full. From there, we get what's called the ideal gas law. PV equals nRT. It's a simple relation of pressure, volume, moles, and temperature. Essentially, we can combine all of our laws to get PV equals NT over NT equals a constant R. That if I combined all of our K factors together, we get that R. Now, there are many different R's, but there's only 2 R's that we will really use in this chapter. R in units of liters, bars per mole Kelvin, or bar liter per mole Kelvin, and liters atmosphere per mole Kelvin, or atmosphere liter per mole Kelvin. These units will convert a bar and a liter, or atmosphere and a liter, to the other units of N and T. However, we could easily calculate and figure out what would the R need to be for a torr. What would the R need to be for a Pascal? So technically, you could do an R for any unit of pressure. But we're going to stick with the 2 most common so we don't have to calculate them. Now, what makes this an ideal gas law? When we say an ideal gas law, an ideal gas is a gas that essentially has no atomic size and no intermolecular attraction, meaning that we're ignoring how all the gases are different. We're saying these gases don't interact with each other, they don't have different interactions, they're all the same size, so we don't have to even include their size, we don't have to calculate their size. We're just saying they're point charges that are bouncing around. We don't have to worry about positive, negative interactions. We're going to just treat them as balls with no little dots with no sort of polar force. Now, this is patently false. Gases have size. Gases do attract to each other. But this holds accurate to most normal conditions. If we talk about our ideal gas at any normal pressure and temperature, it works just fine. And in fact, we can use this to figure out the average volume of a gas. If you calculate the average volume of one molecule versus another, you can figure out, like, oh, how much would 1 mole of water take up? 1 mole of water takes up about 18 mils. 1 mole of oil might be a little different, depending on its weight and density. Well, gases, since they all essentially have the same volume, all have an average volume of 22.4 liters under standard temperature and pressure conditions. When we say standard temperature and pressure, we're saying 1 atmosphere and 0 degrees Celsius. We're assuming the temperature is 0, thus it's 273 Kelvin. So knowing mole is supposed to be 1, and our temperature is 273, and our pressure is 1, we can find that the volume of 1 mole of gas should take up about 22.4 liters. So if I put 1 mole of gas into a balloon, that's how big it should be. Now, so most balloons do not have a whole mole. Either they're very highly pressurized and not allowed to stretch to their full capacity. But okay, so we have our next several slides are just applications. So let's look at this. So 1 mole of argon is stored at 2 liters and a temperature of 300 degrees C. What pressure? And then I say, if under the same mole we have a pressure of 300 psi, what temperature would it explode under those same conditions? So V is still going to be 2. 504. Okay. So with that in mind, let's look at this. It's rather easy. We just have to isolate the variable. We have to isolate the variable. So our equation is PV equals nRT. In equation 1, we are trying to find out the pressure. So our equation converts to nRT over V. With that in mind, N is 1 mole. N is 1 mole. R is 0.08314 bar liter mole per mole Kelvin. Our volume is 1 over, let's see, 2 liters. And our temperature is, if I can change 300 to Kelvin, that's 573 Kelvin. Now let's look. Moles, Kelvin, liters. So with that in mind, what do I have to do? 1 times R times 573 divided by 2. So I'm just multiplying across, dividing by everything on bottom. I get a pressure of 23.8 bars. Equation 2 now asks you to find what is the temperature. So we rearrange it. We say PV over NR is equal to T. Let's convert 300 psi into bars. 1 bar is equal to 14.504 psi. psi. So 300 divided by 14.504 is 20.68. Okay, this is rated for 20.68 bar. We heated 23.8. Not good. Probably going to pop. So we got to figure out what temperature would it pop at. 20.68 bar times 2 liter times 1/1 mole times 1 mole Kelvin over 0.08314 bar liters. Bar liters, moles. So my answer will be in Kelvin. So 20.68 times 2 divided by R. That gives us 497.6 Kelvin. If I turn this into Celsius by subtracting 273, something like 224.6 Celsius. 224. So definitely not no 300. Definitely not no 300. So one more practice problem. We have right here a 20 cubic foot acetylene tank. Not enoxyacetylene, but just 20 cubic foot. So that's a volume, 20 feet cubed. Starts with a pressure of 225 psi at a temperature of 25 degrees. How many moles could be held in that? 14, so 1 atm per 14.7 psi and 28.3 liters per cubic foot. Okay, with that in mind. Okay, so we'll look at this, and this will be the last for this video. So we have a volume, we have a temperature. I have to do some quick conversions. But rearranging PV over RT equals N. I've just rearranged our magical equation. Well, let's see, 20 times 28.3 means this is going to hold 566 liters of gas. 225 divided by 14.7 means it's going to be at compressed to 15.306 atm. And at 225 degrees, this is at 298 Kelvin. So, plugging our numbers in. 15.306 atm times 28.3 liters times 1/298 Kelvin times a mole Kelvin over 0.08206 atmosphere liters. ATM liters, Kelvin, my units will be moles. Where did I get that number? That is a constant. You could look it up. It was provided in the problem itself. So there was no, 566 liters times 566 divided by 298 divided by my R, 08206. That was provided, and so this would hold 354.3 moles. A lot of moles. It holds a lot of moles. But that is where we will stop.